67 called pairs of connectable servers in a weighted tree network. So let's first try to understand the problem. So we are getting an unrooted weighted tree. So this is a tree structure, and we can understand it as an undirected graph. And we're going to have the servers, it is 0 to n minus 1. This means we have 0 to n minus 1 nodes. And we add, so where edges I is a, b, and weight. So for example, node 0 to 1, the weight is 1. So for example, 0 to 1, the weight is 1. 1 to 2, node 1 to 2 is connected, and the weight is 5. So this is just the meaning. And we are also giving another integer. It is called signal speed. So this is very important for us to understand what is the problem. Yeah. So two servers A and B are connectable through a server C. If so, A should less than B, A not equal to C, B not equal to C. So this is understandable. So for example, two servers 0 and 2, and in between there's a server 1, and we're gonna check if server 0 and 2 are connected. It is, yeah, because the distance from C to A is divisible by signal speed, and the distance from C to B. So for example, the distance from 0 to 1, it is 1, modular the signal speed 1, it is 0, and 5 modular 1 is 0. So this means 0 to 2 is connected. Yeah. So if we understand about it, so let's just understand about here. So the paths from C to B and the paths from C to A do not share any edge. So this means 0 to 1, 2 to 1, they didn't share any other edge. So C to B and C to A, they didn't share any edge. So we're going to return an integer count of less n. So where count I is the number of server pairs that are connectable through the server I. So for this answer, so the answer 0, so the index 0, it is 0, because for this node 0, there's no servers connected. Yeah. So for node 1, it is connected with 0, 2, but it is connected with 0, 3, 0, 4, 0, 5, so that is why the answer is 4. So for example, node 2. So for this node 2, it is connected with 1, 3, 1, 4, 1, 5, 0, 3, 0, 4, 0, 5, because the signal speed is 1, the modular always works. So that is why it is 6. I will not use other examples, but I want to use the example 2 to explain how to solve the problem. Yeah, because 2, as we can see, yeah, the graph is a little bit more complicated. So according to this graph, we should know how many nodes and how many edges. So this is the edges. So the edges, number of edges plus 1, gonna be the how many nodes. So for example, the edges we can say it is 6. So the number of nodes is gonna be 7, because it's gonna be 0 to 6. So this is the number of nodes. And we should know that it is connected like a tree structure, but we can solve it like a graph problem. Now, for any node, let's just use this node 0. Yeah. So for the index 0, it is 2. How can we find those two pair? So we can find it is going to be a 6, because 0 to 6, it is 3. 3 modular the speed, signal speed 3, it is 0. And for the right side, we can find 3 and 4. So definitely for this 4, it works. So this means for a pair, 6 and 4, it is one pair. Another pair is 5, because 5, the distance from 0 to 5, it is 6. 6 modular 3, it is 0. And this node 4, the distance from node 4 to 0, it is 3. 3 modular 3, it is 0. So this means we can find a pair, node 4 and 5, node 6 and 4. So we can find two pairs. So let's just check what we are. So this is a 5, 4 and 4, 6. This means we can find two pairs. So now the problem becomes, how can we find those two pairs? So for example, this is node 0. Yeah. So it is just a DFS problem. Actually, it is similar to, yeah, it is similar to the post-order traversal. So for this node 0, we just need to know how many nodes are connected with this node 0. It is node 6 and node 3. So For node 0, we find the valid node going to be node 6 and 5, and this can be calculated. Yeah, because while we are checking this 0, we're going to check this node 6, and for this node 6, we're going to check how many nodes that is valid. Yeah, so this means from node 0, definitely we know that there are going to be 2 nodes that are going to be valid. So it's going to be node 6 and 5. So from 0 to the right side, we're going to check this node 3, it is not valid, and then we're going to continue. This 4, it is valid. This means we find 1, and we're going to continue to find this node 2, it is not valid because 1 plus 7, it is 8. And this 1, it is not valid because 6 plus 1, it is 7. 7 modulo 3, it's going to be 1 instead of 0. Yeah. But how can we calculate from the left or from the right side, from this edge or from this edge? First of all, we're going to turn this tree problem into a graph. So now this is an undirected graph. Now we just need to use the DFS to check how many valid node. But how can we check that? Yeah, this is just a DFS. So from here, for this node, we should know the distance is 3, it is valid. And then we're going to continue. So this is 3 gonna plus, yeah, because while we are traversing the DFS, we're gonna store the value of this 3. So this 3 plus 3, it is 6. This is another valid value, so it's gonna be 2. So this is the basic idea. And similarly for the right side. Currently, the weight is 1, it is not valid. But while we accumulate it to 3, it is valid. While we accumulate it to 7 or 8, it is not valid. Now from the right side we code 1, from the left side we code 2. So in total, it's gonna be 2 pairs. So it's going to be just 2 times 1, it's going to be 2 pairs. So if the right side has 2 nodes, it's going to be 2 times 2. So this is the basic idea. Now let's just try to solve it. And we can use this graph to solve the problem. Yeah. So we're going to prepare the number of vertices. So it's going to be the length of the edges plus 1. And then we're going to prepare a graph, default dict, and it's going to be a list. So for UVW in edges, GU gonna append another edge which gonna be V and W, and GV gonna append another edge, it's gonna be U and W. Now we're gonna prepare a DFS. Let me just write the DFS. So we're gonna write it like this. It's gonna be easier. So the pattern gonna be the first node, which gonna be X. And we're going to prepare parent, and we're going to prepare the first weight. So for example, from 0 to 6, we're going to prepare a weight, which is 3. From 0 to 3, we're going to prepare a weight, which is 1. Yeah. So this is what we passed into the DFS. So currently, I will give a pass because I will calculate it later. Now, let's just prepare the final result. It's going to be 0 times n going to be the number of vertices. Now we're going to check the graph. So for I, it's going to be an array in g.items. Now we're going to prepare a total sum value which is going to be s. Because while we are checking this node 0, from the left side we're going to check the total number of nodes. We're going to check the total number of nodes and times the total number of nodes from this side. Here is 2 times 1, which is going to be 2. But what if there's another branch? There's something else. Maybe here the value is going to be 3. So what is going to be the final result? Yeah, because for this 2 and 1, 2 times 1 it is 2. Now what happens is from this side we already have so the result result is 2. Yeah. Now from this side there's another branch, so the value is 3. So what is going to be the possible result? So it's going to be maybe this node with this one. Yeah, so here going to be a 3 and here going to be 2. So it's going to be 3 times 3 going to be 9, and 9 plus 2 going to be 11. So this is going to be the answer. Yeah, because from this side we should know the total pairs. Yeah, but let's just explain it later. Let's just start coding, I think. this s is going to be a total sum, and then we're going to check for y and weight inside of this array. So for example, this array for 0, and the weight for this weight may be 0 to 6. So the weight is going to be the weight is going to be 3. Yeah, and we're going to prepare a count. So the count is going to be dfs with x and y. Dfs y and parent going to be I. So parent I is 0, and the current node going to be y. It's going to be 6. Yeah, and we're going to use this weight. So this weight is going to be 3. Yeah, so this is the count. Now we can update the final result. So result I going to plus equal to the count times s. So from the beginning, from this side there are 2 nodes, or we should know that the count is 2. There are 2 nodes that is valid. So the count times 0, it is 0. 0, because currently we just use those 2 nodes, it is 0. Yeah. But after that, we're going to update the s going to plus equal to the count. This means the total number of the node. Yeah. So from the beginning, this node is just 0. Now this s going to plus the node 2, so the s going to become 2. Yeah. Now we're going to, from this node 0, check another branch. So for example, this branch here, and we find, oh, there's only one valid node. So what's going to be the result? So the result I going to plus equal to this count. Count is 1, because currently the count is 1. 1 times s. S is 2. So 1 times 2. So currently the answer is 2. Yeah. But what if we have another branch? It is here, and the valid node is 3. So we're going to continue to check. So this s going to be updated to from the beginning. This s is 2, and then s going to plus 1. This s going to be 3. Now what about this count? This count is going to be 3 because we have another branch. I hope you understand it. So this is the hard part of the problem. If you understand that, basically you know how to solve it. Yeah. Now our count is 3. And result I going to plus equal to this count. It's going to be 3 times s. And s we've already calculated before. It means from the, this side, yeah, from this side, how many valid nodes? It's going to be 3. So this is the basic idea. Because there are 3 valid nodes, for example, this 3 valid node. This one with this one, this one with this one. Yeah, definitely we can find that. So it's going to be 9. And in total, it's going to be 9 plus 2, it's going to be 11. This is exactly what I explained before. And this is why we're going to use this kind of coding to update the final result. Yeah, so finally, we just needed to return the final result. But we didn't finish the DFS yet. So let's just finish it. So for y and weight, as we're going to use weight, so here we're going to use total. So we're going to use t. From the beginning, t equals to this w. So for y and weight in graph with x, if y not equal to the parent, so we're going to continue run the DFS. So we're going to prepare a variable count. So count is going to plus equal to DFS with y, and the parent going to be x, and the total weight is going to be this t plus the w. And finally, we just need to return this count. So what is this count? So from the beginning, this count is going to equal to 0 if t modular, according to the problem, we need to modular the signal speed. If it is not equal to 0, so it's going to be 0. Otherwise, it's going to be 1. Yeah. So this, the meaning from here is that, so for example, this is node 0. This is node 6. In between, there's a weight, which is 3. So we're going to use this one. T equal to 3 modular this signal speed. If the signal speed is 3, so it means from the beginning, this count is going to be a 1. Yeah, so this is the idea. And similarly for others. So for example, for this 6 and this another one, so we're going to accumulate all those counts. So this is the basic idea of how we're going to write it like this. Now let me just run it to check if it works. As you can see, it works. Now let me just submit it to check if it can pass. As you can see, it passed for all testing cases, although it is a little bit slow because this is an O(n) squared time complexity problem. So the n going to be 1000. So here for this DFS, definitely this is ON. And from here, definitely we take all the items and all the edges, so this is another ON. Because for the graph, the vertices is equal to the number of edges, because this is a tree structure. So from here, basically, this is the vertices plus all the edges, but we can understand it as ON, because this is a tree graph, tree structure. And from here, we use a DFS, this is another ON. So that is why it is ON square. I think that's all about it. Thanks for watching. See you next time.